Excess burden of labor income tax computation with the help of Matlab using the Matlab program Chapter 5 Welfare Tau L. Hello and welcome back to the third video in a row of 3 videos. In the first 2 videos we have computed the excess burden first in partial equilibrium and then in general equilibrium. So we analyzed what happens to consumption, to utility, if the labor income tax rate in the United States is increased from 23% to 24%, and computed the excess burden. And it turned out that in partial equilibrium we found an excess burden of 4.7% of tax revenue, and in general equilibrium we found a much higher value, 6.8%. So it made a big difference whether you used partial or general equilibrium analysis. Now in the following video we will compute these values with the help of Matlab. Therefore we have to tackle 2 numerical problems, 2 computational problems. The first one is the solution of a nonlinear equation system. The second one is to apply the method of reverse shooting to compute the transition dynamics from the old steady state with 23% to the new steady state with a labor income tax rate of 24%. So let me briefly review the economics, the model that we analyzed. Therefore, let me change into the slides. So you can download the slides that I present in the following from my homepage. And you should also download the computer code, the Matlab code for Chapter 5. And it would be beneficial if you have read through the material in my book on public economics, in particular Chapter 7.3. Now let's go into the part with the labor income taxation and skip to the page with the general equilibrium effect. So we analyze the Ramsey model or neoclassical growth model where the household maximizes intertemporal utility. Instantaneous utility, lowercase u, is a function of consumption C and labor L and is discounted by the factor beta. The utility function is specified as a Cobb-Douglas function, and the weights of consumption and leisure and utility are denoted by iota and 1 minus iota. 1 over sigma denotes the intertemporal elasticity of substitution. The household owns one form of wealth, which is physical capital, and the capital stock K accumulates according to equation 6, so increases with investment IT, which will be equal to savings, and declines with depreciation delta times K. The household budget is presented by equation 7. On the left-hand side we have income, net income. So the labor income WL, which is taxed at the labor income tax rate tau L, interest income R times K, and we spend it on consumption C and on investment IT, which are equal to savings. We can derive the first order conditions for this utility maximization problem, and they are represented by equations 9a through 9c, which are the first order condition with respect to consumption C, with respect to labor L, and with respect to next period capital stock K of tape in T plus 1. We can condense the first two first order conditions to the last equation, which we will call the first order condition with respect to labor. The production side is characterized by a representative firm. So goods and factor market are we have perfect competition in the goods and factor markets. Production is characterized by a Cobb-Douglas technology, where the capital income share is denoted by alpha and the labor income share is denoted by 1 minus alpha. Since we have perfect competition and a constant returns to scale technology, total production Y will be dispensed in the form of income to the households, in the form of labor and capital income respectively, and the shares of labor and capital income are 1 minus alpha and alpha respectively. Profit maximization implies that the factor prices W and R, the wages and the real interest rates, are equal to the marginal products of labor and capital respectively. And the third sector in our economy is the government. Well, it runs a balanced budget, so the total government consumption G are equal to total government tax revenue, tau LWL. So tau L is the only tax in the economy, and government consumption is a pure waste, so it does neither affect utility nor production. We will analyze this case in later chapters of the book. If we insert the government budget constraint 12, the factor prices 11, in the household budget constraint 7, we derive the resource constraint of the economy, so total production Y is equal to private consumption, public consumption, and investment. Now we can solve these equilibrium conditions in steady state and derive the following 6 equations 14. In the 14a, we have the Euler equation. 14b is the first order condition with respect to labor. The factor prices are given in 14c and 14d, the resource constraint in 14e, and total government expenditures G are presented in equation 14f. So this constitutes an equation system in 6 endogenous variables R, W, C, L, K, and G. So when we compute the effect of an increase of the labor income tax rate from tau L to 23% to 24%, well, we solve this nonlinear equation system in 6 variables. And we first have to calibrate the model, and therefore we set the parameters beta equal to 0.96, so that we have a real interest rate after depreciation approximately equal to 4%. The depreciation rate delta is set to 10%. The labor income share is equal to 64%, or the capital income share 36%. This is alpha equal to 36% is a little bit low. So the labor income share is not 64% in the United States in recent years, but has declined from 62% in 1960 to 57% today. But we want to keep in the tradition of these general equilibrium models, which have traditionally used this labor income share. Tau L in the old steady state is the average over the last 50 years, which is 23% in the US. And therefore we have a government share of 14.7% in GDP. And we set the intertemporal elasticity 1 over sigma equal to 1/2. Now how do we calibrate this model? We start from the first equation 14a. So with the help of the discount factor beta and the depreciation rate delta, we can solve 14a for the real interest rate R. Using 14d, we can compute the capital labor ratio, K over L. Given that labor in steady state is set equal to 0.3, we can solve for the capital stock. And this implies production and the labor, the wage rate, W. From 14e, we can compute the consumption, and we use 14b to calibrate Yoder. So we have all the other variables, W, C, 1 minus L, and tau L. So notice how we proceeded in this calibration. So this is a steady state condition in 6 endogenous variables, R, W, C, L, K, and G. Now we can set all parameters except for Yoder with the help of observation from the United States, empirical observation. So to set Yoder, we have to somehow have an additional condition or set any of these endogenous variables, so then we can solve the equation system 14 for Yoder. And we have decided to use the labor L and set it equal to 0.30 to 30% of total endowment with time. We could have used other facts, for example, that consumption share in output is something like 60%. So there the researcher has a little degree of freedom and might use it to its advantage, actually. Now let's get into the problem and into the numerical problem and look at the Matlab program. For this reason, I would like you to invoke the Matlab program. Chapter 5 welfare tau L, and load it into your editor. The first thing you should do is to find out if your program works. So for this reason, press F5 or the green arrow in the top menu bar and let the program run through. So after interim results, I've introduced a couple of pause statements. So for example, here we compute iota with a value equal to 0.3424. And you have to click in the command window and press any key that the program continues. So these pause statements are helpful if you want to note interim results. This interim result here is if the first order condition is actually equal to 0. And here we compute the consumption equivalent change in the case of the partial equilibrium, which is equal to 1.08%. And next we compute the excess burn relative to tax revenues in general equilibrium, which is 1.1%. And finally, we compute the transition dynamics in our model, which look like the one displayed in figure 1. And we will get to this in a minute. And then the program stops by pointing out the utility loss in terms of consumption that accrues during the transition, which is 1.07% of consumption. So let's start to debug the program. For this reason, I would like you to move the cursor into the editor window and click in line 12, the minus sign. Click the minus sign in line 12, where we clear the screen. Now, if we now execute the program and press run in the upper menu bar, the execution stops in line 12 and we can debug the program at will. So at ease. So let's run until line 12 and press step or F10 to execute line 12. As you can see, the screen is cleared and the command window, there's no entry. In the command window below, there's no entry. And next, we just shut down all other variables so that we're sure there are no values for the variables left in our memory, which can lead to misleading results. So this terminates the first part of the program, the step 1 house cleaning. The next step is step 2, the parameterization, which I just showed you in the slides. So we have to choose parameter values for alpha, beta, labor in steady state, sigma, tau L, delta, the number of transition periods for our dynamics from the old to the new steady state, which we specify at the amount of 40. Now we'll find out that this is sufficient, but you may have other applications where this is not the case. Then you have to increase the number of transition periods NT. And the next two parameters displayed utility are just computational parameters, so that Gauss knows if it should display the transition dynamics or not. And we only want to display it and also compute the transition utility here in the final iteration when we have found the solution. So next we use the steady state conditions which were specified in equations 14a through 14f. First we use beta and delta to compute the real interest rate R. Next we compute capital intensity K over L from the marginal product of capital. capital stock is simply capital intensity times labor supply, and the wage rate is equal to the marginal product of labor. Total production is given by the Cobb-Douglas function in K and L, and we display the interim result here for our calibration. So for example, we find an initial capital stock K star equal to 1.2882. And we also compute government share, which is equal to 14.72%, and consumption with the help of the resource constraint. So consumption is output minus government consumption minus depreciation in steady state. And we use all the variables C, W, L, tau L to calibrate our variable iota, which in this program we call gam. Sorry for this little nuisance here. And we find a value of gamma which is equal to 0.3424. So these are the shares of consumption and leisure in our utility, 1.34 and 1.66. So next we need to move the cursor into the command window to press any keys so that our execution can continue. And we store this solution in the variable x initial. Now we will use the next we will compute the partial equilibrium effect. And therefore, let's switch back into our slides. And let me show you how we compute the partial equilibrium effect. Now we want to study the excess burden, compute the excess burden from increasing tau L from 23 to 24%. So this is the marginal excess burden that we would like to compute. In partial equilibrium, we assume that the wage rate W, the gross wage, remains fixed, and that the capital stock also remains fixed. Later in general equilibrium, we will find out, of course, the net income of the household will decline, therefore they save less, and therefore the capital stock will decline. And during the transition, there will also be an adjustment of the wage rate W. In partial equilibrium, we neglect this and just assume W and K remain fixed. So therefore, we have that consumption must be equal to net income plus interest income minus depreciation, and W and K remain fixed, and the household only adjusts the labor supply to L prime and consumption to CT. The second condition to solve for the new labor consumption choice is the first order condition with respect to labor, which is given by the first equation on slide 38. So in the old steady state, labor supply was 30% and consumption was 0.303 for in tax rate tau L equal to 23%. In the new equilibrium, with tau L equal to 24%, consumption and labor dropped, so the new labor supply L prime is equal to 0.2994, and the new consumption C prime is equal to 0.2998. With the help of these values, we can compute the consumption equivalent change. So how much would the household be willing to pay, or by how much does we need to compensate him if we move from the new steady state from the new allocation to the old one. So we get delta is equal to minus 1.07%, meaning that in the old steady state, the household is better off, and he would be willing to give up 1.07% of consumption if tau L is not increased to 24%. Now with the help of C prime, L prime, and delta, we can compute the deadweight loss. The deadweight loss is the consumption loss, 107% times consumption, which is equal to 0.003244, and the additional tax revenue, which are equal to 0.00310. And this deadweight loss relative to the extra tax revenue is equal to 4.7%, our deadweight loss in partial equilibrium. And we look at this computation now in our Matlab program. Therefore, we have to compute the new equilibrium in a procedure, and I will show you this procedure FOC1 first. So let's step in the function FOC1. Here in the FOC1 is a function of labor and consumption, so this will be our L prime and C prime. The capital stock, the wage and the interest rate are the old steady state values, so we just analyze partial equilibrium. And the equation 1 is our first order condition with respect to labor, and equation 2 is our budget constraint. And now we are stopped in debugger, so we need to step out. And our solution will be displayed for the steady state. And of course, it should be equal to 0, otherwise we would have misspecified our function. But this is fine, and we now know that we have made no typing error in the function FOC1. Okay, this introduces another POR statement, and we have to switch to the command window, press any key, and go back into the editor now to continue with step 3 and compute the partial equilibrium effect, the excess burden. So now labor income tax goes up to 24%, and we solved this nonlinear equation system FOC1 for the new labor income tax tau L 24%, which we have stored in the parameter tau L1. And this parameter is transferred to the solution of the nonlinear equations problem FOC1. So we use the Matlab command fsolve, which solves nonlinear equation problems. We have two arguments of our function FOC1. One is our endogenous variable x, which we would like to find out about, which contains labor and consumption. The second argument is the parameter which contains, for example, the new labor income tax rate and the old wage rate and the old capital stock. And we have to specify the argument, in this case it's x, for which this solution system has to be solved. We provide an initial guess for this variable x, which is our old steady state value with labor supply equal to 0.3 and labor supply consumption equal to 0.3035. And the solution of this nonlinear equation problems is stored in sol, in the variable sol. And here you find the solution 0.2996 and 0.2999 for L prime and C prime as presented in the slides. And in the next couple of lines, we just compute the consumption equivalent change and the deadweight loss. So here we compute, first in line 81, we compute the percentage change in the consumption. It drops by 1.19%. Labor supply drops by 0.14%. The consumption equivalent change is equal to 1.08%. And here we now have another pause statement, so switch into the command window to press any key so that we can continue debugging. And we save the values here and continue with step 4, the general equilibrium effect. We do a comparative steady state analysis. So how do we continue to compute the general welfare effects? So let me switch into the slides again. The general equilibrium effects, of course, we have to compute the new steady state. In the new steady state, we have to solve here equation 14a through 14f for the new value of tau L equal to 24%. So again, we have to find the solution of a non-linear equation problems. With the new values L double prime and C double prime, we can again compute the consumption equivalent change, which is 1.1%, the new tax revenue, and the deadweight loss relative to the additional tax revenue, which is 6.8% in general equilibrium. So let's go back to the Matlab program and continue our debugging here. So we analyze the steady state equation. Therefore, let's step into this steady state, the function steady state, by pressing F11. So here we have the steady state conditions. We have 5 endogenous variables: labor, consumption, capital, wage rate, interest rate, and we have 5 endogenous equations. So I've already replaced the endogenous variable government consumption G here, and I've inserted the fiscal budget in the resource constraint. Let me show it to you here. We have tau L times labor times W in the resource constraint, so we can express our steady state now in 5 conditions in the 5 endogenous variables C, K, W, R, and labor L. And the 5 endogenous equations here, the 5 steady state conditions, are the first order condition with respect to labor, the resource constraint, the 2-factor prices, and the Euler equation. And now we can just step out of this function. And as you can see, for the old steady state values, this equation system, this function, is equal to 0. So we have programmed it correctly, typed correctly the 5 steady state conditions, so everything fine here again. So let's continue our debugging. Again, another pause statement. And now we have to compute the new steady state for the new value tau L1, which is equal to 24%. So we store the value tau L1 here is now, as you can see in the parameter, equal to 0.24. And for this parameter, we solve again this nonlinear equation system steady state, which has 2 arguments: the variable x for our 5 endogenous variable that we would like to compute, and the parameter values for the labor income tax rate and our parameters beta, delta, iota, and so on. And the nonlinear equation system is solved in line 101, and we have the new variables for labor supply, consumption, capital stock, wage rate W, interest rate R, and the variables are 0.2995 for labor, 0.2998 for consumption, 1.2861 for capital stock, 10815 for the wage rate, and 0.1417 for the interest rate prior to depreciation. With the help of these variables, we can compute government consumption the relative change of the percentage changes of consumption 1.2% and labor 0.1.6% in steady state. So, and the consumption equivalent change, which is equal to 1.10% in general equilibrium. So it's higher in general equilibrium, this comparative steady state effect, than in partial equilibrium. And now we have again to switch command window to press a command, any key. So this terminates the computation of the partial and general equilibrium effects for the excess burden. Now in the second part of this video, we look at the transition dynamics.